Hello and welcome to part 2 of the tutorial on statistics. So in this tutorial we'll talk about probability theory, which is the math behind statistics. So in case you're following at home, this is the notebook you should open and then you can run the cells. Remember, go in View, in Edit, and clear all outputs, so that we're starting with a fresh notebook. Okay, so I'm going to switch to the outline now. So what is this tutorial going to be about? Is about probability, a general introduction, and random events, so like flipping a coin, things like that, and about probability models in general, and we'll talk about two particular examples: the uniform distribution and the normal distribution. So that's probability in general, and specifically for statistics we're going to talk about samples. So when you have a random sample, you can talk about the properties of a random sample. Okay, so let me reduce the size of my face now so we can see the notebook clearly, and let's get started. So the concept map gives you a general overview. So the probabilities all in this box. Probability model is the main building block. Probability distributions and their parameters. So note, probability models, the parameters are usually Greek letters. And what we're going to use probability models is to model populations and to model the sampling process, how the statistics of random samples, what can they tell us about the population. And the whole process here of inferring properties of the population from a sample is called statistical inference. But this is for the next video. For now we're just building the tools. I want you to have the math tools, so when we talk about them in the next section you'll be ready. Okay, so in general, probability is a way to describe uncertainty, variability, and randomness. So it's a very general purpose tool. We're going to give examples with a coin flip and rolling a die, so basic random events. Not because they're super important, but just to get a feel. Like, this is random events, it's kind of new. If you've never seen random variables before, it's good to see them in something really simple. And in fact, this is historically how probability got started. Mathematicians went to the casino and were like, oh, how do I how do I calculate the games of chance? So that's how this historical start. The modern probability is so much more than that. You have all kinds of math models that describe different scenarios. The noise, so when in a communication channel, you can model the noise, different levels of noise using probabilities. Statistics, the notion of taking random samples and assignment, all of that. So as I just said, statistics is built on probability. So you can't skip this section and just say, oh, give me the formula. You need to know what's going on. As a side benefit, probability is used not only in statistics, but in physics, machine learning, their biology, their optimization, there's randomized algorithms. It's good stuff. Okay, so let's get started. This needs to be hands-on, not... let me restart the kernel so we're really sure. Restart kernel. I want the numbers to start at 1. Okay, so these commands just import some libraries that we'll need. NumPy, pandas we already saw in the previous, and for the plotting. Again, ignore this part. Okay, let's get started. So the random package, the random module in Python provides the function random.random for generating random numbers. In particular, the standard random number is between 0 and 1. So you can think of this as a simple building block that you can use to build other random processes. In the first example, a coin flip. Well, let's run it. So you see, we get 0.85 as the output. If you run it again, you'll get a different output. So this, if you're a programmer or if you've ever used a calculator before, usually you put in numbers, you get specific number out, right? The calculation, what you input, you get the same thing out every time you run it. But not for random numbers. That's the whole point. You get a random number out. Okay. Next, let's build a coin flip based on this randomness. So this gives you a number between 0 and 1. So if we split that space in half, we'll get half the probability. So if it's in the first half of the interval, we'll say the coin flip is heads. If it's the second half, we'll say tails. Right? And int works. Every time you run it, it will flip a coin. In this case. Okay, let's flip it 10,000 times. Okay, so this line flips the coin 10,000 times. Here we select only the heads, and the proportion is 50% about. So the coin seems to be working. This is a slightly more complicated version. Multiply by 6 and convert to an integer. And now you get a random number between 1 and 6. Okay. Let's see what happens if we roll 600 dice. So that's the totals. So we expect 600 to be 100 each. But in fact, we see there's 95, some are larger than others. So that's reality. You know, when you a random process, we want it to be roughly equal among the 6 outcomes of the die, but it's not guaranteed. What we do know is if we keep increasing the number of rolls, you see now they're close to 1,000. There are only this one is a bit larger. This one, if we go to 60,000, it's pretty close to 10,000 each. So a little bit foreshadowing, when you take larger and larger samples, the probabilities get more and more uniform, close to their expectations. So that's a very powerful idea that you cannot, in random processes, even if you can't predict individual outcomes, you can, the long-term averages, you can predict. Okay. You can read this for details, but the main reason we need probability is to model the distribution of data. So if you have a population, we can fit a mathematical model. So we can choose a mathematical model to describe the population. So that is a big factor. And another factor is analyzing the sampling. So what can you expect if you take a sample from a population? What are going to be the properties of the sample? There are two other aspects you can read about that, random selection and random assignment. So here the uncertainty is a disadvantage to us. We have to deal with it. We're trying to sort of bound it and analyze the variability in data. And here it's another type of, we're using randomness for our advantage, to our advantage. By random selection, so when you're choosing the samples from a population randomly, you can make inferences about the whole population. And the other aspect, random assignment, is what Amy did with the employees. Remember that we split them into two groups, either their group statistics or group no statistics, completely random. So if we find differences between the two groups, if they were, for all other purposes, they were similar, then we can attribute the differences to the statistics training. So we already touched a little bit about that, but all this to say that randomness sometimes helps us. It's not just we're trying to deal with randomness. Okay? So at a very high level, the new concept here in bold is a random variable. So probability theory, we describe quantities that are uncertain. The specific value of x, capital X, is uncertain. Instead, we have a distribution. So we know what range of values it can take on, and we'll see that in a second. Note the parameters of the distribution are usually denoted with Greek letters. So if you see theta or mu or sigma, something like that, it's all parameters of the model. Okay, so there are all kinds of probability distributions, math models, real-world events, right? The best kind is the math model. So we know everything about it. So once you know the probability distribution, you can generate random numbers, you can transform it, you know everything there is to know. And other cases are when you can sample from it, you can get numbers. So you can read the details of that. Okay, first example. Example 1, the uniform distribution. So this is the simplest distribution. We already saw it. Random.random gives you a uniform, it gives you a random number between 0 and 1. So the way to denote this, so this is how I'm going to create. So there's a function called uniform in SciPy stats distributions. And I say, give me a uniform between 0 and 1. And now this object has all the methods that we need from a random variable. The method RVs is called random variates. It's used to create 10 samples, to draw a sample of size 10 from that. And you see there are a bunch of numbers between 0 and 1. Just like we saw above, but we're doing 10 at a time. If we plot the distribution, it looks like a flat, so it's constant between 0 and 1. All the weight is between 0 and 1, and 0 probability outside of this range. Within 0 and 1, all the numbers are equally likely. That's why it's called uniform. So every number has the same probability of occurring between 0 and 1. So that's an example. There are dozens of probability distributions. This was the simplest one, so that's why I'm showing it as an example. The second distribution you need to know about is called the normal distribution. Gaussian, bell-shaped curve. It's super important. Let's see it. So you see why it's called the bell-shaped curve. So this one in particular, I created it here. I said create a random variable with mean and standard deviation, with mean 1000 and standard deviation 100. So if you look at the width, so the standard deviation is roughly the width of the bell. How wide is it? If you want to make it narrower, we can set this to 75. And you see it got squeezed a little bit. If we want to make it wider, we can put 200 here. So you see it's the weight includes, it's a much more variability, right? In the middle is still 1000, but now the numbers go all the way to 1400 and to 600. You know, it's spread out. I'm gonna put back the 100. Okay, so the normal family is denoted here with this calligraphic n, it's not just one distribution, right? Every distribution, there are two parameters, the mean and the standard deviation. So whenever we talk about a normal function, all the properties we talk about apply in general to all the distributions, all the distribution in the normal family. So the formulas we'll use maybe will be different for different distribution, but the shape in general is the same. Okay, what can we do with that? So if you know the density, so this equation here is encoded in behind this function. So P of x is PDF, probability density function. So let's say you're wondering what is the probability of seeing a number, the outcome being between 800 and 900. So that's what I've drawn here, the shaded region. The probability of that, of a number coming in this range, well, we have to do the integral. So the density is the blue line, so the total probability is the area under the curve. So we can obtain that using integration. You say integrate this function, the density, between 800 and 900. If you've never seen integration before, it's just computing the total. So the total area of this region. So because the total area under the curve is 1, so total probability, and we're just interested in the shaded region here. So you're not missing anything. Okay. Speaking of integration, so every time you want to do a probability calculation, you have to do an integral. So what if we pre-compute the integral? Then it will be easier, no? So that's what the cumulative density function does. So it computes the area as a function of the input x. So f of x is the total probability up until that lowercase x. So it computes the integral as a function of the upper limit. So when you have that, the same question, we're interested between 800 and 900, what's the probability? You can obtain that answer by just subtracting the CDF. So this is the integral all the way to now 900, and this is the integral from 0 to 800. So we subtract them to get the shaded region. So if you're familiar, people familiar with calculus will recognize this is the basic rules of so the differences in the antiderivative give you the value of integrals. Okay, there's another function here, so called PPF, the point percentile function, which gives you the inverse of this function. So if you want to know how far do I have to go in here to reach 60%, so this would be 50%, so I have to reach somewhere around here, the answer is 1025. So the area up until here, 1025, contains 60% of the weight. And you can check what is the cumulative distribution. So yeah, I mean, very often we'll need this inverse of the cumulative density function. So Python provides you the function PPF for that purpose. Okay, so that's in general, you can compute probability for any outcome. In particular, there are two common scenarios, the bulk of the distribution and the tails. So let me show you. If we go 2 standard deviations away from the mean, this shaded region contains 95% of the weight, more than 95%. So this is very useful in practice because if you want to know a region, an interval of values that you can expect the value to fall. So right? It's random. It could be anywhere between minus infinity to infinity, but you see the center of the distribution, most of the weight is between 800 and 1200. So this region here contains 95% of the weight. Sometimes when you report answers that are normally distributed, you can say, hey, I don't know where the outcome will be, but I know it will be between here and here 95% of the time. So this is called a confidence interval. So that's a convenient, so what is this region is, it's not 200, it's really 2 times, you see the formula we're computing is 2 times the standard deviation. So if the normal distribution was different, maybe more narrow or wider, you could still use this formula. The numbers will be different, but if you go 2 times away from the 2 standard deviations away from the mean, and 2 standard on both sides, that region is 95% of the weight. And the tails of the distribution describe the complement of this. So you see what remains here and here, here shaded in red, right? So if we go greater than, more than 2 standard deviations away from the mean, the sum of this density, this probability in this, the total red is 0.43. So less than 0.05, which is 5%. And this is the opposite of what we talked about above. It's the rare events. If you're uncertain about this random variable, and you say, well, the probability of observing a value in the red region is pretty unlikely. So the concept of 5% or less is a common thing, rule of thumb in statistics. Like, well, this is highly unlikely. It's very surprising to see a number fall outside in the red region. Notice it's not exactly 5%, it's like 4%. So if you want to say at most 5%, you can use two standard deviations. But in many, to be more precise, you can say 1.96 standard deviation. So like quite a, that's the, if you want to be precise, to get 5%, this is the number you want to use. Okay, good. So far, so good. All right. Now we enter the most important part. So this was, all of this we talked about one random variable. And the probability, what kind of values it can have. Imagine you have, instead of 1, you have n copies of it. So you draw one, you draw another, you draw another, n copies. So that's a random sample. So you have identical copies, n of them. And why do we care about this? Because this is what we do in statistics. We're going to obtain samples. So we're setting up the math. We need to define the math tools to work on samples. In particular, statistics. So remember that a statistic specifically is a function computed from a sample. So the sample mean and the sample variance are two most common examples. And remember the formula for the sample mean, 1 over n times the sum of the values. And the sample variance is the squares of the difference from the mean for each value. But here is a convention that I didn't talk about, but it's really important. Capital X is a random variable. So this formula that we've written here is not a particular numbers we're putting in here. We're putting a random variable. So each of these can take on any number of values, right? It's the whole range. We just saw all these distributions. So the expression here itself, the mean, the average, the sample mean, is itself a random variable. So this is really new. Like when people talk about previously, if you talk about the mean of a list of numbers, that's a specific number. It's not an expression. But this thing, capital X, or the overline, so the overline means average, this is itself a random variable. Same for the sample variance. This whole thing is a random variable. That's what I'm saying here. So it will have a distribution. And the name of that distribution is called the sampling distribution. So as you get different random samples, you're going to get different value of the sample mean. So when you, the distribution of the sample mean depends on which particular values you're going to observe. Since they're random, this is going to be random. Okay, so here is a copy of this. Just to understand how this is going on, we're going to do some examples. So the function mean, the average, takes the sum of the values, divides by n, the number of them. Very simple, right? 3 plus 3, 6, 12, divided by 3, 4. Not too complicated. Okay, so now we're going to try to explain the sampling distribution. So sampling distribution is perhaps the most important concept in this whole, in the whole book, in fact, and the most difficult to understand, unless you write it as in using programming. So what did we say? This function, the capital, or let's talk about this function mean. We want to evaluate it for a random sample. So so here we're talking about the mean, but in general you can talk about the sampling distribution of any statistic. And when you compute that statistic of a given sample, you get a different number out. So the sampling distribution says, well, what if I keep repeating? I get a different sample, compute the statistic. Repeat, get a different sample, compute this. So that's the sampling distribution. How capital X is not one sample, but infinite number of samples. We can approximate the sampling distribution by drawing 1,000 samples, or 10,000, or some finite number, just enough to get a distribution. Okay, so how we're going to build the sampling distribution is draw a sample, and it depends on the size of the sample. So here we're saying sample size n, compute whatever function it is, whatever statistic on that sample, and that's it, just record it. So the sampling distribution is the output of the statistic for different samples. So let me define that. And we're going to use it in 1 minute. Before we use it, let's define, redefine again the uniform distribution, right? Random variable 1. Okay, so here is 30 samples of size 10 from the uniform distribution. As you can see, all the points fall within the interval 0 and 1. So each of this is a different sample, but when we plot them, we end up with uniform distribution. So now that was the raw sample data that were shown as points. Now imagine for each sample we compute the mean of the sample, so the average value of each sample. So for this point, this point, this point, the average is going to be somewhere in the middle. For the other points, it will be somewhere else, and so on. So that's what this function does. It tells you for a given sample from the uniform distribution of size 10 here, we want to compute the mean. So find me the mean and plot the distribution. Okay. Okay, so it takes a little bit of time, but in the end we get a histogram. So the average of 10 points is it's another point, and then we repeated that 10,000 times to get a distribution of all these points, of the averages of the samples. And this is interesting. So the distribution itself, the samples are uniform between 0 and 1, but their average turns out to be normal. So this is one of the interesting things that occurs everywhere in nature. Every time you have a sum of lots of independent variables, the normal distribution comes about. So, for example, the height, human height, genetics, there are thousands of factors that determine height. And when you combine them, it's all different partial influences, influence from this, influence from that. So in the end, depending on the genetics, the distribution of height within a population is normal. So same with in physics, for example, or in biology, many other areas where you have an outcome is dependent on hundreds or lots of independent factors, a normal distribution will come out. So this is the most clean example that the uniform distribution, look, it's completely uniform. The average of a sample from the uniform distribution turns out to be normal. And as a little bonus, we can analyze this distribution here. We can find its mean and its standard deviation. Its mean is 0.5, so the center, right? If you have a uniform distribution, the numbers are equally likely to be on the left or on the right of the middle. So the average will be in the center, 0.5. And the spread here is almost 0.1, 0.09. We know the width. So that's cool. We have seen, so if we ever compute, so we know what happens to the average from this distribution. Let's repeat that, ignore that for now. What we did here was with the uniform distribution. Now we're doing it with the normal distribution, 1,000 and 100. And you see here they're not uniform. There are more values in the center and less towards the tails. So this is, again, 30 samples of 10 values each, of size 10 each. And we have a distribution. We have, so that's random variable 2. And we want to find the sampling distribution of the mean. So it's exactly the same function, but now we're feeding it this variable. And what do we get? Another normal distribution. So, but very different. So this one was pretty spread out, versus this one is all concentrated, very concentrated here in the center. I mean, this distribution, each of these values here is the average of 10 values here. So for sure it will not vary that much, right? The variability of the sample is large, but the mean, the average of, it's like the center point, center of mass of 10 points, it's going to be somewhere close to the middle. Again, the distribution can be above or below 1,000, but the average is going to be pretty much in the center. Same thing, the spread of this, so the center is very close to the real 1,000, the middle, and the spread is about 30. Okay, so we see two different distributions, the uniform and the normal, and when we take samples of size 10 from them and compute the mean of the samples, we see a normal distribution come out. So that's you can try that, by the way, at the exponential distribution. For any other distribution you can try. When you take large samples, 10, 30, 40, 50, the average of each sample, the average, when you compute the averages, they will be normally distributed. So this is really weird that the normal, somehow the mean of any sample turns out to be normal. And this observation is called the Central Limit Theorem. So it tells us two facts. The first fact is that what we just described, the sampling distribution of the sample mean is normally distributed for any random variable. And as n increases, so larger and larger samples, it becomes very close to the normal. So depending on how the shape of the distribution, if you take small samples, it will look like normal, but not quite. But starting at n equal to 30 or 50 for sure, it will look exactly like a normal distribution. So that's a general, in other words, the average, the mean of any sample is normal. So that's part of the central limit theorem. The second half is even more precisely. You know this width of the distribution? Well, if you know the variance or the standard deviation of the original variable, the original random variable, then the standard deviation of the mean of the sampling distribution, so of the mean, it will be related with this formula. So as n increases, the width of the sampling distribution gets closer and closer. So we can illustrate that here with this example. So this is the same distribution. The points here represent the sample. So these are 50 samples, repeated 50 samples. And the red point represents their average. So you see, with 3 points, the points can be all over the place, and then their average is somewhere in the center, but you see the average moves around a lot. When you get samples of size 15, again, the samples are all over the place, but the average of the samples, the red dot, stays pretty stable in this center. If you look at the histogram, again with the points, this histogram combines all the red points and plots them in between these two lines. You see it's pretty spread out. For n equal to 15, it's more concentrated. You see it's narrower. And then if you take samples of size 200, look at the mean. The mean stays very close to the center, right here. So this phenomenon, the larger the sample, as the sample increases, so the variability of the sampling distribution gets smaller and smaller. So this aspect is why we have statistics. Without this, we wouldn't be able to estimate anything. Like the fact that you can, taking a large sample allows you to make very precise statements is the basis of all of measurement. You know, when you repeat a measurement many times and you average the results together, they have less variability than the individual measurements. So intuitively, each sample, each data point makes a mistake or has unexplained aspects to it. And when you take a large sample, then you start to get to the real average. And you can get more and more precise with large samples. Okay, so let's quickly go back. So we're done, but I want to go and verify this formula. So, okay, so we already saw that the sample mean will look normal. We saw that for the uniform, we saw that for the normal. But there's a specific prediction here that whatever the population, the random variable variance, standard deviation, when the sampling distribution will be 1 over square root of 10, right? Because we did samples of size 10. So let's check that, okay? So for the uniform, this was the sampling distribution for samples of size 10. And we measured here the width to be 0.906. And the central limit theorem tells us it should be the standard deviation divided by square root of n, the sample size. And it's pretty close, 0.91, 0.91 here too. So not perfect, but pretty damn close for sample of size 10. And the second, for the normal, the sampling distribution of the mean is also normal, with width much tighter than the original variable. Let's see that the width was 31, and the central limit theorem predicts that width will be 31.6. Well, not quite, but you know, pretty accurate for an approximate result. So that's what I wanted to cover in probability. We saw the normal distribution, and we saw a particular example, the sample mean. When you compute the sample mean from a larger and larger samples, these converge to a very narrow distribution. The variability of the sample mean gets smaller and smaller. Okay, so this was just a setup, because in the next chapter on statistics, we'll need this probability. You need to really be familiar with the normal distribution. We'll use it repeatedly. So, to be continued in the next video. All right, ciao for now.